For this lecture, we are going to cover examples out of only section 1 in chapter 5. So it'll be a little shorter than the previous ones because we only have this one section to cover this module. Okay, so a handful of the problems that we are going to work on. The first one here is out of section 5, coming from problem number 2 out of section 5.1. Okay, so this problem asks us to take into consideration we have a 20 kilogram mass that is attached to a spring, and it gives us the frequency of a simple harmonic motion at 2 pi cycles per second. And we want to determine what is the spring constant rate, what is the frequency of that simple harmonic motion if we replaced it with the 80 milligrams of mass. Okay, and so for this problem, it provides us that our mass is 20 kilograms and that F is 2 over pi cycles per second. So the first thing we want to do is find our K. So we have F is equal to 1 over 2 pi times the square root of K over M. We know that we're solving for K, but we know that M is 20. So in this case, we have 1 over 2 pi square root of K over 20 is equal to 2 over pi. We're really just trying to simplify this problem out a little bit. We can multiply both sides by 2 pi in order to, because ultimately what we're trying to do is get K by itself. So when we do that, it cancels here in the numerator and the denominator. And this is going to leave us with, I don't know why I put 20 here. It should be 2 pi. And so this is going to cancel the pi's out here, and that will leave us with the square root of K over 20, make that better, is equal to 4. Now to get rid of that square root, we can multiply or take the square of both sides. And so that will leave us with K over 20 is equal to 16. Lastly, we can multiply both sides by 20 to get K by itself. And we get that K is equal to 320. And that's the value of the spring constant. Okay. Now to find the frequency of the simple harmonic motion, we want to let K equal that 320 and M equal 80 as given in the last line of our problem here. And so our F then in this case, right? So F in this case is going to be the square root of 320 divided by 80 times that 1 over 2 pi. And so that's going to give me 1 over 2 pi times the square root of 4 if we simplify that. Well, the square root of 4 is 2. So that is going to give me 1 over pi cycles per second. Okay, next problem, number 6. We're looking at a force of 400 newtons stretches a spring 2 meters. Excuse me. And a mass of 50 kilograms is attached to the end of the spring and is initially released from the equilibrium position with an upward velocity of 10 meters per second. We want to find the equation of motion. Okay, so the equation of the spring mass system with no external force for an undamped force is going to be our M double prime plus, or you can write it however you want. Some textbooks write it as the dy over dt squared. Some will write it just as y double prime. They're all the same thing. ky equal to 0, okay? We're also given that our y0 is, our initial value at y0 is 0. Our v0 is equal to our y prime of 0, which is equal to that 10 meters per second. Okay, so we were given that the mass is 50 kilograms, right? So we know our mass is 50 kilograms. And we have 400 newtons stretch the two springs, stretches the spring 2 meters. Therefore, we have that as well, right? So given that, we can put this all together using our formula here, where we know that we have the 400 newtons is equal to K times, and we knew that we were stretched 2 meters. So that gives us that K is 200 meters per second. So the equation for the spring mass system then is going to be 50, right, for our mass. That's, we're really just plugging it up into that equation up at the top, d2y over dt2, plus our K, we calculated, or the K is what we actually just calculated here, where we have the 200 right there. Y is equal to 0. Okay. And again, just remembering what I wrote up here, where we have our Y of 0 is equal to 0, and our V of 0 is the same as 10 meters per second. So when we put that into the equation here, we end up with, if we want to get this 50, if we divide everything, this whole equation by 50, we get d2y over dt squared plus 4y is equal to 0. So our auxiliary equation then is going to be that m squared plus 4 equals 0. And when you factor that using the quadratic formula, we get m is equal to plus or minus 2i. Okay, so therefore y of t is a cosine of 2t plus b sine of 2t. When we're looking at y of 0, we have a cosine of 0 because that's 2 times 0. So I should probably just put the 2 times 0 plus b sine 2 0. Okay. So we get that y of t then is equal to b sine of 2t. Okay. Taking the derivative of that, we have y prime equals negative 2b cosine of 2t. So y prime at 0 equals to 10 gives me then that negative 2b is equal to 10. So b is equal to negative 5. So my equation would be y of t equals negative 5 sine of 2t. Okay. Next problem, this comes from problem number 34. We have a mass of 1 slug is attached to a spring whose constant is 5 pounds per foot. Initially, the mass is released 1 foot below the equilibrium position with a downward velocity of 5 feet per second. And the subsequent motion takes place in a medium that offers a damping force that is numerically equal to 2 times the instantaneous velocity. We want to find the equation of motion if the mass is driven by an external force to the f of t equals 12 cosine 2t plus 3 sine 2t. Okay, so if we're looking at this, we have our x double prime plus 2x prime plus 5x equal to 0. So really that auxiliary equation, m squared plus 2m plus 5 equals 0, will give me m equal to a -1 plus or minus 2i, again, using that quadratic formula to get there. So we have x of t is equal to e to the -t times our c1 cosine of 2t plus c2 sine of 2t. When we look at this at x of 0 equal to 1, then we have e of -0 times c1 cosine 2 times 0 plus c2 sine 2 times 0. We get that this is going to be c1 is equal to 1. Okay, do the same thing for plugging in our x prime of 0, and that is equal to 5. So that gives me then 2c1 minus 1 is equal to 5. Therefore, c2, sorry. Therefore, c2 is equal to 3. So our overall function then is going to be e to the -t times cosine of 2t plus 3 sine of 2t. Okay. Next problem, we are looking at problem number 35 in your textbook. We have a massive slug of one slug when attached to a spring, stretches it 2 feet, and then comes to rest at the equilibrium position. Starting at t equals 0, an external force equal to f of t equals 8 sine 4t is applied to the system. We want to find the equation of motion if the surrounding medium offers a damping force that is numerically equal to 8 times the instantaneous velocity. Okay, so we have that our mass is equal to 1. We know that our dampening constant is equal to 8, right? And if we apply Hooke's law, we get that F is equal to -kx, right? Where F is our force, X is the extension in length, and K is the constant. And acceleration due to gravity gives us that 32 feet per second squared. So we have 32 here is equal to -k times 2. Therefore, our K is equal to -16 pounds per feet. However, we can omit the negative here because we really just want the magnitude. So we can just say that our K is 16. Next, we'll want to use Newton's second law. Okay, and using Newton's second law, this is where our mass, our m is going to be that mass attached, and our beta is going to be 8. That's that positive damping constant. So we have m d2x over dt squared equals negative beta dx dt minus kx plus our function. Okay, we can rewrite this so that we can have our function to the side by itself. So we're really just rearranging so that we can have our function is equal to what? And our function is equal to d2x over dt squared plus 8 dx dt plus 16 is equal to our function, which is that 8 sine 4t. Okay. So from that, we can see that our x sub c is going to be d squared x dt squared plus 8 dx dt plus 16 is equal to 0. Okay. And we also can, from that, note that our xp, our particular, is double prime plus 8x prime sub p plus 16x sub p, I'm going to make this sub p a little better, is equal to our 8 sine 4t. And let's just turn this, take the next slide. Okay. So what this then gives me that my m squared plus 8m plus 16 equals 0. I could factor that as m plus 4 squared equal to 0. Therefore, m is equal to -4. So essentially, you could think m1 is -4 and m2 is equal to -4. So that gives us x sub c equal to c1 e to the -4t plus c2t e to the -4t. Okay. So now when we're looking at our particular, we have x sub p is equal to a cosine of 4t plus b sine of 4t. So the first derivative of that is going to be -4a sine of 4t plus 4b cosine of 4t. And then the second derivative is going to give us -16a cosine of 4t minus 16b sine 4t. Okay. So if we look back at the equation that we used over here, and just copy that and bring it to our next page here. Now we can use that and the three things that we just computed to put that all in place. We have a negative. I'm going to just actually copy instead of rewriting. So we're going to copy, paste that. That takes care of this piece right here. Okay. The next one, 8 times the second one. Okay. So copy and paste. Plus 8 times that second one. Plus 16 times first one. Okay. And all of that is equal to our 8 sine of 14. Okay. So essentially what we're looking at here then is that, let me see if I could save us a little bit more room. So what that gives us then is we have this -32 a sine of 4t plus 32 b cosine of 4t is equal to 8 sine of 4t. Really, that was just from simplifying all of that from above. So we can say that -32a plus 0b is equal to 8. And 0a plus 32b is equal to 0. Therefore, a equals -1/4 and b will equal 0. So our x sub p is equal to -1/4 cosine of 4t. Okay. So when we put that into our general equation, we get that x of t is equal to our sub c function and plus our y sub p here. And now really all we have left is make a little bit more room. Is if we had x of 0 is equal to 0, then that gives me, plugging all of that into our equation up here, that's going to give me that 0 equals C1 minus 1/4, because your e to the zeros equal 1, and when you have t equal to 0, this term here kind of just goes away because of the 0, and all of that. So that then gives me that C1 is equal to 1/4. Okay. When we do the same and we plug that, if we look at our second derivative, plug in the 0 as well for that, we will solve out and get that 0. That we get 0 equals -1 plus C2 plus 0. So C2 is going to equal 1. So our equation then is going to be 1/4 e to the -4t plus t e to the -4t minus 1/4 cosine of 4t. The next problem is problem number 37. We have when a mass of 2 kilograms is attached to a spring whose constant is 32, it comes to rest in the equilibrium position. Starting at t equals 0, a force equal to F of t equal to 68 times e to the -2t times cosine 4t is applied to the system. We want to find the equation of motion in the absence of damping. Okay. So in this case, we know that our m equals 2. We know that k is equal to 32. And we know that beta is equal to 0. We also know that our function f of t is equal to 68 e to the -2t cosine 4t. So m d2x over dt squared equals -kx minus our beta dx dt plus our function. Okay, so this is 2 d2x dt squared equals -32x minus 0 dx dt plus 68 e to the -2t cosine 4t. Okay, so we have m squared plus 16 equals 0. Okay, so our x equals c1 cosine of 4t plus c2 sine of 4t. Our x sub p is going to be e to the -2t times a cosine of 4t plus b sine of 4t. And then if we do the first derivative, second derivative, like before, remembering that the derivative of cosine is negative sine and the derivative of sine is cosine, we can put into play 4a minus 16b is equal to 34, and 16a plus 4b is equal to 0. So then we would solve that a is equal to 1/2 and b is equal to -2. So our x sub p function is e to the -2t times 1/2 cosine of 4t minus 2 sine of 4t. Okay, so our overall equation, x of t, is going to be our c sub c function, right? But we know then that what our C1 and C2 are, we can calculate this at negative 1/2, and we could have calculated this one at 9/4. Okay, plus we can distribute this e to the negative 2t to give us 1/2 e to the negative 2t cosine of 4t minus 2 e to the negative 2t sine of 4t. Okay, next problem, problem number 50. This one is we're given, we want to find the charge of a capacitor given some conditions here. Okay, so we have L Q double prime plus R Q prime plus 1 over C Q is equal to E. Okay, plugging in the values that we were given, we gave that L is equal to 1/4, plus we were given R is 20, plus C was 1 over 300. So this is 1 over 300. So that really is just 300. And E is equal to 0. Okay, so we can multiply the whole thing by 4, and we'll get Q prime by itself plus 80 Q prime, or Q double prime is by itself, plus 1200 Q is equal to 0. If we let Q equal E to the MT, we'll have our M squared plus 80M plus 1200 equals 0. And that'll factor as M plus 60 times M plus 20. Therefore, M equals negative 60 and negative 20. So we'll have that our Q of T is equal to C1 e to the negative 60t plus C2 e to the negative 20t. And Q prime equal to 0, Q prime evaluated as 0 is equal to 0. So that gives me here, if I do Q prime of T, that is negative 60 C1 e to the negative 60t minus 20 C2 e to the negative 20t. So 4 plus C1, 4 equals C1 plus C2, and 0 equals negative 60 C1 minus 20 C2. So in this case, C1 equals 4 minus C2. And over here, we end up with 60 C1 plus 20 C2 is equal to 0. Plug in what we have here for C1. So we have 60 times 4 minus C2 plus 20 C2 equal to 0. And simplify this, we get 40 C2 equals 240. So C2 is equal to 6. We can come back and plug that back in over here. And we get that C1 equals 4 minus 6. So C1 is equal to negative 2. So our general equation then is negative 2 e to the negative 60t plus 6 e to the negative 20t. Okay, the last example out of this section I have for you is trying to find the steady state current of a LRC series circuit, okay, given the information that we have here. So very similar to the previous problem, we use L Q double prime plus R Q prime plus 1 over C Q is equal to E. Plug in what we know 1/2 Q double prime plus 20 Q prime plus 1 over 0.001 Q is equal to 100 sine 60t plus 200 cosine 40t. Okay, so in this case, we will do our Q sub C is equal to e to the negative 20t times C1 cosine 40t plus C2 sine of 40t. Okay. Our Q sub P is going to be the A sine 60t plus B cosine 60t plus C sine 40t plus D cosine 40t. Okay. When we plug in the values, we end up with negative 1600A minus 2400B times that sine 60t plus 2400A minus 1600B times cosine 60t plus 400C minus 1600D sine of 40t plus 1600C plus 400D cosine of 40t, and all of that is equal to 200 sine 60t plus 400 cosine 40t. Okay, that gives us that A is equal to negative 1 over 26, B equals negative 3 over 52, C equals 4 over 17, and D equals 1 over 17. So our steady state charge our steady state charge then is Q sub P negative 1 over 26 sine 60t minus 3 over 52 cosine 60t plus 4 over 17 sine 40t plus 1 over 17 cosine 40t. Okay, problem asked us for the steady state current. Okay, and so that is I sub P of negative 30 over 13 sine 60t plus 45 over 13 cosine 60t plus 160 over 17 sine 40t minus 40 over 17 cosine 40t.